Okay. Welcome, everybody.
Wait, this is everybody?
I mean,
like
I guess. I'm assuming, though.
Well,
let me check the actual attendance. I feel like the lights need to be brighter.
No, I like it right there. I like the other color way better also.
It gets rid of the gel.
Yes.
Yeah.
Attendance. Ryan's gone. Alexia's gone. Oh, if anyone's in contact with Alexia, I think I have her paper that she was asking about. It's just on, it had no name on it. It's on the no name board.
I thought you meant like sitting next to it, like we have to go to the nurse or something.
Oh, no. Kylie, Max, Channing, yeah. This is us today.
Well, Max is sick, but he has to get tested, so that's why he's not here.
No. Yeah.
I heard there's a.
No.
Me and Farjar were laughing about the school's website said there's only one case of COVID in the school.
Yeah, that's definitely not updated.
Well, I'm sure there's more. There just aren't getting tested.
Yeah, but we know about more than one, even without people getting tested.
Yeah, I guess it's probably fair.
Right? Okay, we're going to finish these slides today. We are going to talk about intermolecular forces, which sounds very daunting and cool. That's because it is. Okay, so we talked about polarity. And we know that some molecules are very large and they can have polar and nonpolar regions within them. Okay, intermolecular forces is the last topic of this unit. There is an online, like, virtual lab game thing that I might want to do regarding this topic. If that looks, I'm going to check it out tonight. If it looks good, we'll do it tomorrow. Monday, I think, is a lab. And then I think from there is like review test. So I'm planning on the test being on Wednesday. But if we're totally lost about this, maybe we'll push it back a day. We'll see. But planning on a Wednesday test. And I'm getting a new marker. Try blue. Okay, intermolecular forces. This is exciting stuff. Okay, so far we've only learned about chemical bonds, but there are other attractions between atoms that we need to talk about. Okay, they're called intermolecular forces. So if I were to make a spectrum of atoms being attracted to each other, chemical bonds is all the way on one end where they're permanently attracted and they're bonded together. On the other end of the spectrum, there are these attractions that are not permanent and they don't make new compounds, but they're still significant enough to affect the properties of the compound, and those are intermolecular forces. There are three of them that we're going to learn about today. London dispersion forces, dipole-dipole interactions, and hydrogen bonding. These are in order from weakest to strongest, as indicated by the slide. Oops. Okay, so we're just going to go over these three types of interactions that molecules can have with each other. He went underneath today. Interesting. Ready to jump in? No. Okay. You don't really have to write this. You don't have to write any of this, honestly. I promise, Esme. London dispersion forces. Okay, these are attractive forces between all molecules ever. Any molecule, whether it's polar, nonpolar, whatever it is, will have London dispersion forces, okay? And these are attractions that are due to random electron movement, Okay, so I'm going to draw a little diagram here to kind of illustrate how this works. We're going to do, let's do ethane. C2H6. Okay, and I'm going to draw two molecules here. Okay, so I've got two ethane molecules, and they're just hanging out together, and we're going to imagine I've got like a whole sample of ethane, so there's trillions of other molecules, but we're just going to look at two for now. When I draw this as a Lewis structure, we are modeling the electrons as being localized in very specific places. I think I've mentioned this before, but the reality is that electrons are not just stuck in one spot, just like frozen in space, just like hovering there. In reality, they fly all around. If we think of individual atoms, we know that each individual atom has its own electron cloud, and the electrons are moving around in unpredictable paths. That doesn't go away when I have a molecule. If I have all 8 of these atoms bonded together, yes, we write little lines to show that there's electrons here, but in reality, I have an electron cloud around the entire thing, and the electrons are moving around the whole molecule randomly. Okay, that's hard to draw, so we do the lines, but in reality, they're flying everywhere. We don't know exactly where they are at a given moment, but we know they're there. Okay, so we can think of like a molecular electron cloud around here. And what happens is that because those electrons are moving around randomly, over time, they will spend an equal amount of time in different areas of the molecule, but in a given split second, they might be unevenly distributed. So in one specific given moment, if I like stop the clock and just like take a snapshot of it, I might at one split second have a lot of electrons on this side and then maybe only a few on this side, just for a split second, like for a nanosecond or something. Okay, now if I have just for this one moment in imbalance electrons, what do we think happens to this molecule momentarily? If I have an imbalance of electrons, it's polar. Now it's not permanently polar, but for a split second it is. So if I have more electrons on this side, what charge do I have over here? Slightly. Negative. I have a very slight negative charge on this end, and I have a very slight positive charge on this end. It's going to go away in another nanosecond, but for now, it's here. Okay? And so what this can do is, because this is polar, and this is nearby another molecule, the electrons in this molecule are affected by that. And so if I have lots of electrons here, those are going to repel the electrons here. It's going to push them away, and maybe for a split second, I'm going to have lots of electrons on this side and maybe only a few over here. So now for a split second, this molecule is very slightly polar. So what happens when I have a positive and a negative nearby? They're attracted for a very short amount of time, and then it goes away. Because the electrons are moving, they're going to move back, and the attraction is going to go away. But for a split second, I have an attraction between these two molecules. Okay, that attraction is a London dispersion force. Okay, and these are happening and then going away, and then happening and then going away, all throughout the molecules of whatever sample of whatever I have. They're always happening. Oop, I'm clicking the wrong thing. Okay, so it's a momentary dipole, and it leads to a transient attraction. I like the word transient because it's there, but then it goes away very quickly.
So does this really like affect anything major?
It does. I can't prove it to you, and I didn't discover this, but apparently this is how chameleons are able to stick to things they climb on. Literally, the London dispersion forces between their little fingers or toes, or whatever you call them, causes them to stick just enough to whatever they're grabbing that they can climb around and do stuff like that. So yes, for them, this is very important. They're able to climb with this. And this is the weakest force that we know about or care about between molecules, and yet it's significant enough that it helps animals climb and survive and stuff like that. So yes, it is significant. For chemists, this will affect things like the boiling point or how gooey something is, like viscosity. So it affects the physical properties of the compound. Okay, so every molecule, no matter what it is, will have London dispersion forces. Okay, so if I give you a list of molecules and I say, which of these has London dispersion forces? You say all of them, or you check all the boxes, or whatever way you answering that question means all of them, that's the answer. Okay, so very easy. Now, that's not to say the London dispersion force is equal for all compounds. The larger molecules will have stronger London dispersion forces. So if I give you maybe a handful of molecules or two of them to compare, and I would want to know which one has stronger LDFs, you just pick the bigger one. Okay, pretty straightforward. Do we know why the bigger ones would have stronger forces? Why does that make sense?
They're just
Mass?
Or mass, maybe. Like, that's true, but does that affect the strength of this force?
They're probably made up of bigger atoms that have more electrons, so there's more.
Yeah, bigger atoms, or just more atoms in general, even if they're not bigger atoms. If I just have more carbon atoms, there's more electrons. Also, I have more space to maybe shove more electrons into a smaller space. If this molecule was twice as big, I could have twice as many electrons and then for a split second have them all in one little area. And so the amount or level of polarization I can get is higher with a bigger molecule. Okay, so in general, larger molecules have stronger LDFs. Okay, so that's London dispersion forces. They occur with everything. Okay, questions? Okay, that's the weakest intermolecular force that we care about as chemists. The next one, dipole-dipole interactions, is a little stronger. Okay, this one has a typo. The last thing here should be polar molecule. Let me change it real quick, sorry. Bam, technology. There's going to be two situations where we could have dipole-dipole interactions. The first situation where this can happen is between two polar molecules. A good example of a polar molecule could be carbon monoxide. This is also a good example because this is an exception to something we've talked about, so I'm going to bring it up. I'm going to tell you this is a polar bond. It's a polar molecule. Which direction does the little polarity arrow point to, though? I have a vote for oxygen. Why toward oxygen? Why would we say that? It's more electronegative. It's going to pull electrons toward it. For some reason, this one's backwards. Okay, so carbon monoxide is the one where it's actually backwards. And the thing that actually tipped this off to me, one sec, Jay, is that if we look at formal charge, if I were to calculate the formal charge of these, oh, I have too many electrons on here. Is that what you're going to say?
Yeah, I was like, what's up?
Telepathy, it's a thing. It should be like that, right? Thank you. Yes. Now it's good. Okay. Still, the formal charge, this is a -1 formal charge, that is a positive. So the dipole moment is actually that way. So it's still polar, but this is the one where it goes backwards from electronegativity. So sorry, there's exceptions to everything. Welcome to chemistry, people. But anyway, we've got this polar molecule, and we have the correct Lewis structure drawn now. Unsurprisingly, I've got a positive and a negative. What do you think they do? They attract. Okay, that is called a dipole-dipole interaction. I've got a dipole here. Okay, dipole is just another word for a polar molecule. I have a dipole here, polar molecule, they attract. Okay, why would that be stronger than a London dispersion force? Why would that be stronger?
Because isn't that temporary?
Which one?
The London dispersion.
Exactly. London dispersion force is temporary. This is permanent. This is always a dipole. This is always a dipole. So you could say you could think of the attraction as like it's always on. It's always there. Okay. And they're able to move away from each other. But if I have more carbon monoxide molecules, they're just always going to be attracting. Okay, so that's dipole-dipole interactions. Another example where this could happen would be between a polar molecule and an ion. Okay, so a good example of this would be dissolving something in water. So let's say I have like a copper ion. Okay, and if this were chemically correct, I would need some anion to go with it, but we're just going to ignore that for a second. And let's say I have water. Okay, we know water is bent. Okay, water is a polar molecule because it has polar bonds, and those bonds are asymmetrical. Where does my arrow point for that molecule? Based on how I have it drawn. Yeah, up toward the more electronegative atom. Yeah. Okay. So here I have partial positive charge, partial negative charge, and here I have a full-on charge. This is not polar, this is a full-on 2+ charge. Okay? And so if I have a polar molecule, one end of this is going to be attracted to that. Okay? And we can see that it's probably going to be that negative end there. And so if I dissolve this copper ion in a sample of water, the water molecules are going to congregate around it because of this attraction. So if I were to kind of draw a kind of a simplified version of this, I would have water molecules surrounding this ion because of these opposite charges attracting. Okay? On the water, it's a partial negative, but it's still enough to be attracted to the positive copper ion, the cation there. Okay? So this is another example of a dipole-dipole interaction. I've got a dipole here. I don't know if I would call this a dipole, but the point is that I have charges that are attracting each other. Okay? But this is not a chemical bond. I didn't make like a copper-water molecule, but it's still an attraction, and the water molecules are floating around. And maybe one of them floats away, but another one's quickly going to fill its spot. Okay? So it's not a new compound. It's not a bond, but it's still an attraction that's strong enough to affect how the water behaves around that ion there. Okay? We okay with this? Okay, so these are the two situations where I could have a dipole-dipole interaction. Okay? And they're stronger than London dispersion forces because the dipole is permanent, it doesn't go away.